Hello, so we are moving into chapter 5. So this is going to be probabilities. So we're going to do this in two parts. The first, we're going to talk about basic concepts of probabilities. Okay, so we're going to talk about constructing sample spaces, how to basically find probabilities. So we actually have two kinds of methods that we have empirical and we have theoretical. And then we're going to talk a little bit about simulations. We're not going to do it too much with a simulation though. Let me change this a little bit. A probability experiment is one in which we do not know what any individual outcome would be, but we do know how a long series of repetitions will come out. So we can't necessarily predict one event, but we could predict several events. I'm trying to grab this little highlighter here. So like I said, so what we hear is that we can't figure out an individual outcome, but over a long period of several outcomes, we could probably tell you what was going to happen. And the more and more and more and more repetitions we have, the better our probabilities are going to be about particular outcomes. So for example, if we toss a fair coin, we do not know. So by fair coin means it equally lies heads or tails. It's not weighted. But if we toss a fair coin, we do not know what the outcome of a single toss will be. It could be heads, it could be tails. We don't really have any good way of predicting that. But we do know that the outcome for a long series of tosses will be about half of the tosses should be heads and half the tosses will be tails. Let me just this a little bit here. And the last bit is the probability of an event is the proportion of times that the event occurs in the long run. So for a fair coin, that is one that is equally likely to come up heads or tails. The probability of a heads is 1.5, and the probability of tails is 1.5. And that's over a long run. Like for one toss, that probability is whatever it comes up as being. But if I toss a coin 100 times, I expect that about 50 of those times it should come up heads. So law of large numbers, got to move some stuff on my screen here. Law of large numbers says that the probability, this is a probability experiment. If it's repeated over and over again, the proportion of times that a given event occurs will approach its true probability. So this is an experiment that sometimes gets done where we toss a coin. So if I toss a coin once, it's either going to be 100% of the times it's going to get heads or 100% of the times it's going to be tails based off one coin flip. So that probability is way off. If I toss it like 2 times, it's likely that both times are going to be both heads and my probability is still going to be 100% of the time heads. Or it's possible that I could get a tail, and then at that point I would be 50% of the time it's a tail. But can't force it to be one or the other. And what we see happens is that as we keep tossing that coin, the probability kind of bounces a whole lot. So here it's 50-50, and we're bouncing around that 50-50. But as we toss that coin more and more times, we see that we get closer and closer to that probability of 50%. Like I said, we might hit it periodically here and here, but what we're looking for is in the long run, we sort of level out and we just stay at about 50%. So that's what law of large numbers is telling us, is that the number of times I repeat an experiment, the closer and closer and closer I get to the true probability. And that is for like a sequence. I keep getting that same probability. I'll hit it periodically here, but I'm talking long run. I'm definitely just approaching it. And at some point, I'm going to stay pretty much at 50% all the time. Not going to be this periodic thing. So law of large numbers is not looking at like when does it happen. It's like if this goes on for infinity, at infinity, 50% of my coin tosses should be heads. So just to make this a little more concise, probabilities are more about predicting events in big systems and not about predicting events in singular scenarios. So we can get really good at predicting, large scale things going on. because we have a lot of data to go into it and tell us what's going on, but we really have a hard time predicting a singular scenario. And we frequently like completely miss on those. So for a good example, let's say you were going to go get some sort of surgery and they're told you the probability of surviving this type of surgery is 95%. So what that means is that if a very large group of patients were getting this surgery, say 10,000, I would expect that 9,500 of them are going to survive. So 95% we expect to survive. However, for the individual, you don't have, it's basically your choices you have is either you survive or you don't survive. So like for an individual, it's really up in the air. I can't really tell you the probability on it. It's a lot harder, but I can tell you long run with a bunch of people, I could say, 950 out of 10,000 will survive. One person, I really can't tell you because I can't say, like you have a 0.95% chance a person will, pass kind of thing. So one person is just really kind of up in the air. It's likely to, really your two choices are it doesn't happen or it happens for you. So we have a problem that we tend to look at probabilities as, if they tell me I have a 95% chance of surviving, then I'm definitely going to survive when that's not true at all. So sample space, the collection of all possible outcomes of a probability experiment is called your sample space. So in the last case, like the surgery, your sample space is either you survive the surgery, you don't survive the surgery. So simple sample space can be something very simple like that. If I toss a coin, the sample space, all my possible outcomes is I can flip a coin and it comes up tails or it comes up heads. If I roll a die, when I roll it, it's likely the face that comes up is either going to be a face with a 1, a 2, a 3, a 4, a 5, or 6. There's not really other options out there. The selection for a student at random from a list of 10,000 at a large university, that sample is going to consist of all 10,000 of those students. So a sample space, like I said, it could be like simply like something can happen and something can not happen. It could be choosing between heads or tails. It could be just coin flips. It could be those students. There was one of like flipping a cup and seeing how it lands. Well, that one's a little more complicated because it can land on its top, it can land on its bottom, it can land on its side. So it's just all the possible ways an event can occur. So we are often concerned with occurrences that consist of several outcomes. For example, when rolling a die, we might be interested in the probability of rolling just odd numbers. So even though we know we can roll a 1, 2, 3, 4, 5, or 6, the outcomes that I'm actually interested in would actually just be these outcomes of 1, 3, and 6, because those are all my odds. So a collection of outcomes of a sample space is called the event. So this is my sample space. And a lot of times when we have a sample space, we just put S to mean sample space. Oops. I can make another event. It just does this. It just captures these numbers. And that is going to be my event. So it's just going to be a part of your sample space. It's the part of sample space you're interested in. I could have potentially other kinds of events. My event could be something really simple, like maybe I just roll a 4. Maybe I roll a 3 and a 4. That would still be an event. It could be I just roll my even numbers. Or it could be just be I'm going to roll any kind of number that is greater than 2. So there's several different events we could find in a particular sample space. We just have to specify what it is we're looking for. So in general, if A denotes an event, and sometimes we use E as another common one, but if A denotes event, the probability of event A is denoted by PA. Probability of event A. once we have a sample space, we need to specify a probability of each event. This is done with a probability model. We use the letter P to denote probabilities. For example, if we were interested in if we wanted to note the probability that a tossed coin lands on its head, then we'd say P heads. So we don't always like make our event necessarily A or B. Sometimes you might see it as PA. A is a toss ahead. There's different ways you might see it, but sometimes we put in just in those parentheses the event that we're interested in. We end up using this probability notation a lot in statistics because we talk largely about probabilities. But like I said, probability notation, probability of event A. Sometimes we use equalities, inequalities, or words to represent an event. So like we said, the probability of a coin getting ahead would be P heads. The probability that I roll a die and it lands on a 3. We might say P x is equal to 3, or we might just say P3. If we're looking at something like the probability that someone is under 25 years old, we might say Px less than 25. So sometimes you might see, like I said, equalities or inequalities, or sometimes it's just words or just a number to represent your event. There's a lot of ways that we represent events.